So yeah, let's start. So let's go over some basics of snark formalism. So a snark is typically defined by this triple algorithm, which is SPV. So S is generally when we set up the circuit. So S of C is the setup of the circuit, and it outputs some public parameters and the verifier parameters. And these parameters are both these parameters are public, and these are used by one by prover and one by verifier. So we have prover parameters and verifier parameters. So this could be, so these are related to the length of the circuit. So if you remember that whenever we compose a ZK snark, we first have to specify the length of the circuit, and this is the ingredient for these parameters. So after that, the prover will take this prover parameter X, which is the statement which he wants to prove, and witness is some private input or private input which he wants to prove the computation of. So the prover will output a proof pi, and then we have the verifier algorithm, which takes the verifier parameters, again takes in the statement X, and it checks whether the proof is valid or not. So it takes the third input as this proof pi, and then it just outputs yes or no given, which represents if the proof is valid or not. So yeah, so X is the statement. Yeah, so I think we covered most. So now we have these different protocols. So we have Groth16, long, and these protocols result in short proofs, but their prover time is n log n, which is slightly larger than linear. And the other protocol, which is Fry, this is most famously used in Stark provers. And this is a fast prover, but it outputs a very large proof. So the question we want to ask is that, can we have the best of both worlds? Can we have like a fast prover, and also can we have like a prover which gives a short proof? So for that, let's go into Snark recursion, and we'll see that how a two-level recursive Snark can solve our problem. It can give us a fast overall prover, and it can also give us a short proof. So in Snark recursion, we have this inner prover, which takes some statement X and some witness W, and it has this, it runs the circuit C of X and W, and this should be equal to 0. So this is the statement, or this is the circuit that prover wants to prove. And the proving algorithm outputs this proof. And along with the proof, we have a verifier, which takes this public, which takes the statement and the proof. So this is the general snark, right? So now let's see if we can put another snark on top of this. So again, what we do is that we pass the statement X to another prover, which is P prime, and this is the outer prover. So this outer prover takes the statement X, and instead of taking a witness, it takes this proof pi. So it is proving that the prover knows some proof, which will output in some statement. So now the circuit does not consist of witness, or it consists of witness, but now the witness is just the proof pi from the previous step. And again, we have that after the prover, we will have a verifier algorithm, which will verify that the outer proof, which is pi prime, is valid proof given the statement X. So again, in the outer proving system is actually proving that the prover knows some inner proof, which is pi, which in conjunction with some statement gives a valid proof. So as we discussed, that how can we have a fast prover with short proof? So what we can do is that we can have this inner proof, which is a fast prover. So because this inner prover is working with the original circuit, so generally these circuits can be very large, have like million constraints. So we want a fast prover which processes the circuit and outputs a proof pi. And as we discussed, that this proof pi will be a larger proof. So this will be like 100 kilobytes. So also I want to make the point that we care about proofs because we care about the size of the proof because we have to commit this on the chain. So the size of data is very crucial to us. So now, given that we have a large proof, but it was processed very quickly by this fast prover, we can again run this through some outer proof system where we have a slow prover, but the output proof is small. So again, we'll have this outer proof, which will take the circuit as X, and the witness will be just the inner proof. And the circuit is just the verifier circuit of the inner proof system. So this is just verifying that it knows proof pi, which such that the inner verifier is valid. So this is kind of a crucial point that in a two-level recursive Snarks, the circuit for the outer snark is just the verifying circuit of the inner snark. So now we will have a fast overall prover, but this will result in a short proof because we only care about the outer proof, which validates the inner proof or proves that the inner proof is valid. So is there any question up until now? So now let's see how do we prove knowledge soundness. So for that, we'll just go over what knowledge soundness means and how is it defined. And this will be, so let's start. So we have a circuit which is defined over n tuple of field elements across m tuple of field elements, where the n tuple represents this X statement and the m tuple represents the omega witness. And this will output 0 for the circuit. So let's assume that. So the concept of knowledge soundness is a bit tricky. I don't think I understand fully right now. So yeah, Guo, if you find something issue, then you can just stop me and correct me. So we prove this knowledge soundness by assuming that, say, suppose we have an adversary A, which can convince the verifier that the proof is valid. So the adversary does not know the witness, so he just can convince the verifier with some probability that that he knows the valid witness for some statement. So given such adversary, there always exists some extractor E. So E is just a extractor algorithm, and it is also known as knowledge extractor. So what E does is that E extracts the witness from the prover. So in the statement, we have that the probability given some circuit which takes statement Y and omega witness, we have extractor which can extract the witness, and the probability of this should always be greater than the probability of the malicious prover, which can convince the verifier that he knows the valid witness, minus some negligible probability. So again, so first when I saw this, I thought that we can extract the witness. How is this like a valid zero knowledge proof? But this extractor this extractor has more capabilities than the verifier. So the way the extractor extracts or pulls this witness from the prover is by repeatedly interacting with the prover and repeatedly querying the prover for some inputs. But this is not done by verifier, right? So verifier just takes gives some challenge and just accepts something from the prover, and then it verifies. So yeah, so the main point is that the extractor is kind of a hypothetical quantity which helps us to define that some prover actually knows this witness. So so this does not exist. The constructor does not exist in real scenarios. Is that clear, Guo? Yeah, you can help me a bit if you see
Yeah,
something.
I think it's clear. Yeah.
Okay. Yeah, so now we have to see how we can construct this extractor from in this recursive proof or in this two-level recursive proof system. So we have to assume that both the inner proof and the outer proof are knowledge sound, so that there exists some extractor which can extract this witness from both the proofs. But yes, but we'll see there is a subtle point. So before that, as I mentioned before, the circuit so the outer proof runs verifies the circuit, which is just same as the verification circuit of the inner proof. So now we have to convince ourselves that we have some extractor which can extract the witness from both these, which can extract the witness which was originally fed into the inner proof system. So again, if we go back to the previous slide, we had some witness which was inputted into the prover, and then the final proof just takes the inner proof as a witness. So the extractor would have to dig through this witness, find this witness from the inner proof. So the way knowledge soundness is defined is that, so say suppose we have, so S prime, P prime, V prime is the outer Snark circuit, and given that the outer Snark circuit is knowledge sound for some circuit C prime, we always have some extractor E prime, which can extract the witness. And remember that the witness in this case is just the inner proof. So this can extract the inner proof and such that the circuit is satisfied. So again, the C prime is again the verifying circuit of the inner proof. And so if you see this extractor kind of is same as the prover because it can extract the witness proof. So it can extract the proof. So it can be essentially seen as a prover because it can output some proof pi from the circuit. So now if we go into the inner proof system, we can we assume that again the inner proof system is knowledge sound. So we have SVG, and this is knowledge sound for some circuit C, such that we will always have extractor E, which can extract the witness from the prover or from the E prime. So again, we are just iterating through the extractor and convincing ourselves that at each point we can extract this witness. And because we can extract this witness, this is knowledge sound. Yeah, so this concept is a little, it's not that easy. It's a bit tricky, but yeah. Yeah, and again, to repeat, the main point of the extractor is to just convince ourselves that our proof system is valid, or to convince ourselves that the prover actually knows some witness, because we will always have this extractor which can extract witness by repeatedly interacting with the prover. So So in our case of two-level system, we have that our final extractor is composed of the E prime and E, which are the extractors at each level of the recursion. And now we have to prove that this whole thing is knowledge sound. And we'll do this by the official definition. So the definition for knowledge sound is that the probability that the extractor can extract a witness omega is this probability should also always be greater than the probability of some malicious prover convincing the verifier that the proof is valid minus some negligible epsilon or error. So now to prove that our two-level recursive snark is knowledge sound, we have to prove that the probability that given the original circuit X and omega, we have that there exists some extractor E double prime, which can extract the original witness from this two-level recursive snark. And this probability should always be greater than the probability that the malicious prover can convince the verifier that the proof is valid minus some probabilities, which is E prime and E. So we can see this equation hold because the first the probability that the malicious prover can convince the verifier minus epsilon prime is just the probability of the extractor. So this is the probability that the extractor can extract witness pi from the circuit C prime equals to 0. So since this extractor, the probability of the extractor is always greater than this verifier, this statement will hold. And again, the outer, if we look at if we include the epsilon, the other epsilon, this will just be that the probability of the extractor can extract the witness omega. So this is the extractor of the inner proof system. This is greater than the malicious prover, which is trying to verify which is trying to convince the verifier. So we are just doing so we're just convincing ourselves that the final extractor is knowledge sound by repeatedly using the probabilities of the inner extractor and the outer extractor. So now there is a subtle point that the time which it takes for the extractor should always be polynomial time, right? Because we want to have these proofs operate in polynomial time. So now if we assume that the time which it takes for the outer extractor is 2 times the time which it takes the malicious prover, then the time for the original extractor will be 2 times 2. So this will be 4 times the malicious prover. So I think, yeah, so this factor 2 is just an assumption that we just have, so given some adversary A, the extractor algorithm runs in some integer multiple of this adversary algorithm. But even if the extractor is integer multiple of the time of the extractor is integer multiple of the time for the adversary, we can run into trouble once the number of recursion becomes very large. So say suppose we have 10, 100 and like very large n-level system, then the time for the extractor will blow up and it will be 2 to the power n times the time which it takes the adversary to convince the prover. So this won't be good. So this will result in the prover this will result in the proving time being very large. So we don't want that, right? Yeah. So so the recursion, I think, is only limited up till some depth. Like we cannot go up to arbitrary levels. And I think so recursion depth, usually we take it to be some logarithm of this security parameter. And yeah, I don't know much details about this. So yeah, so this security parameter lambda, what is this? Yeah, do you know something about it? How is it related to the proof system?
Okay, Lambda is a security parameter. For example, like if we use BN 244, the elliptic curve. So the security bits of that curve is 100 bit. So I think Lambda kind of is the abstract value of this security bits of some primitives that you choose. For example, the hashes, the elliptic curves, or the bit length of your keys, private keys, something like that, or the characteristics of the field, the finite field, something like that. So lambda kind of is just a abstract value, but we have to have to define such value, but not so accurate.
I see. So usually, how do they define recursive depth like that? So say suppose, I don't know, maybe in Halo or in any system where you have this large number of recursion, how do you define this recursive? How, because we have to restrict, we have to only work until those levels. So yeah.
Yeah, I'm not quite sure about that. I think it's still a somehow open problem of because it uses a lemma called the forking lemma. Forking lemma. That for this recursion, that the forking lemma will be, something like you just thought you talked about. So the extractor is not polynomial time, but generally, people thinking that okay, it's still safe if I'm not quite sure about the if it's appropriate or not, but just people just use it. So yeah, if n is a constant, that is not a problem. Yeah, I think there's this discussion in the paper of Nova or some paper before that. There's just those discussions about that. So I'm not the expert of this part.
Okay. Yeah, so I think let's so we are kind of like 1/3 in the lecture. So let's go and try to see the paper, I think.
Yeah.
Yeah, so before I at the first time I saw this paper, this was so intimidating. Like, what do these things mean? But yeah, after going through the lecture, it becomes much more simple. Yeah, so in the paper there are a bit of a bit different formalism, but okay, let's see if we can. So let's start with this NARC on interactive value of argument of knowledge. And so okay, yeah, so this is the security parameter lambda which we are talking about, and we before instantiating the circuit, we input into this G algorithm, it outputs some public parameters. And and this public parameter with some input structure is given to this scale algorithm K, which outputs this public key and verifier key. So this is the public key and verifier key are used by the prover and verifier. So in my presentation, I was using this as just public parameters or verifier parameters. So this is a different formalism, but mostly it's the same. So the prover takes again this public key, some statement U, and witness to give some proof, and then the verifier does the same. Yeah, so knowledge completeness is defined by this statement that the probability given that we have this algorithm, given that we have this prover, and in the initial setup algorithm, that we will end up with this verifier, which is valid, it should always be one. So it's trying to say that we should always have a verifier which can output a valid proof, given which can output which can validate a proof given the initial proof conditions. And this is the extractor algorithm that we're talking about, that the probability of some malicious adversary. Let me see. Yeah, so here A is the PPT adversary, it just stands for polynomial. I forgot what was the other one. Probabilistic polynomial time adversary. So the adversary can, so given that we have some adversary, there always exists some extractor E, such that the probability of the malicious adversary convincing the verifier is some negligible value. So Guru, this statement, this probability given that the verifier that this is a valid malicious. So there should be a subtraction here, right? That's what I'm not able to understand. What's
Yeah,
happening?
it's yeah yeah, the fourth line, right? There's their extractor, right?
Yes,
Yeah,
yes, correct.
yeah, this is here. And saying that for any for some public parameters PP, and the adversary can choose arbitrary SU and pi. I think it literally means that for any SU and pi. Or we can say that SU and pi chosen by adversary, whatever he wants. Then the K is a setup, right? Setup generate the PK and the VK. And from the structure, and then the extractor is able to extract the witness from. Yeah, I think so what's our problem? What's our question?
Yeah. So my question was in the in the knowledge soundness definition, we have this statement, right? That the extractor should always give a witness, and the probability should be greater than the malicious prover, which can convince the verifier, minus some negligible quantity. But if yeah, so when we look at the paper, I'm trying to match this. Yeah. So I think this is kind of included where this extractor gives that witness. So I think given we have a
yes, I think it's equivalent.
Okay.
Because if this probability is negligible, implies that for any witness extracted from the extractor will surely satisfy the relation R.
Okay, okay. So this probability is actually sum of the malicious adversary and the extractor probability.
Yeah, if the extractor successfully extract something,
Extract the witness.
yeah, extract the witness outside, then the probabilistic of if the witness satisfy the relation R is obvious, it should be successful. So that means the opposite part is that the unsatisfaction is negligible. Is it clear?
Yeah, that's so okay. So it's trying to say that okay. So if we have some valid extractor and uh, then this malicious prover will be only able to convince the verifier with some negligible probability. So it will be very hard for the adversary if there was some extracted algorithm.
Sorry, can you repeat?
Yeah. So I'm trying to rephrase this statement, like what it is trying to say. So I think that if we have some extractor which can extract this witness, in that case, the probability that the malicious prover convinces the verifier, that probability will be very small. It will be very negligible.
Yeah, yes. You say that the left side PPSUW don't belong to relation R. So if we change the notation, not belonging to belong to, so I think that the whole probabilistic should be equal to 1.
Okay.
Right, because it's the negation of the, or sorry, the opposite or something like that.
Yeah. Okay. So this relation is so this relation is the valid relation
Yeah,
of
it's
a statement and witness, and the malicious prover just has some other concoct some witness or statement, and that should be negligible. Okay. Yeah. Okay.
yeah,
No,
saying that the any witness extracted successfully from extractor should be valid. Yeah.
Yes. Yeah, this concept is like very tricky. So let's yeah, so most of the protocols that we have been discussing were these non-interactive interactive protocols, right? Where there is some interaction between the prover and verifier, and this interaction usually happens when the verifier gives some challenge to the prover, and prover computes this challenge and submits to the verifier. But we want to convert these proofs into the non-interactive version where the verifier and prover does not interact, and they are their own standalone quantities. So to convert a interactive proof system into a non-interactive proof system, we use this Fourier-Summy transform. And this Fourier-Summy transform, what it does is just uh, it replaces the prover and verifier, the interaction between a prover and verifier with this random oracle. So now instead of interacting with each other, they interact with the random oracle. So in a non-interactive proof system, for the verifier and the prover, we'll have these random oracle gates or some computation which resembles this feature. So so now there is a problem in a proof system, right? Because the verifier has some random oracle gates, or the verifier needs to communicate with this random oracle, but the prover cannot handle these. The outer provers, the outer proving system cannot let the verifier into. Yeah, it cannot handle this computation, right? So what we try to do is that we at before recursion, we remove all these random oracle with some hash function. So I think this is also like an application issue, that in theory there exists random oracle, but in application we rarely use random oracle in applications. So we always substitute this random oracle with some hash function like SHA-256, and we have to assume that our proof system is valid. So the main point was that because the verifier has to interact with this random oracle, the outer proof system cannot handle such queries, right? So that's why we remove all these random oracle gates with some concrete hash function, and this is decided before recursion. So once there is some fixed hash function or some fixed computation, the prover can the outer proof system can process this inside the Snark. So are there any questions up until now? So there is even a bigger problem. So we'll see. So because the outer proof system has to work with the circuit of the verifier circuit of the inner proof system, uh, there there can be there are issues when these circuits are defined over some different field elements. So let's review some basic concepts. So again, our circuit is defined over some some statement x, which is just an n tuple of field elements, and it is defined over some witness w, which is just m tuple of field elements. And now the prover has to prove that he knows some witness such that the circuit outputs to 0. And the way it is usually done, so we have seen this in the past protocols, that the prover will commit to a polynomial and he will encode the computational trace as the coefficients of the polynomial. So here the prover, suppose the prover commits to some univariate polynomial, which has p elements which has p finite field elements. And usually this commit we can use like KZZ commitment, or I think IPA commitment also for this. And yeah, so in this commitment we will commit to some polynomial which is an element in this in this field element of in this field of order p. So p represents the number of elements in this field, and the field is defined over some group. So the order of this group is p, and whatever computations we do, for the prover always does arithmetic in this group. So it will do some addition, multiplication in regarding this group. So Gu, I had one question. So in this representation, we have this that so FP is represents some field field with some P elements, and this Y it. So what I'm trying to ask is that how is this a univariate polynomial? Because the field element does not take. Okay, okay, I see. So the field element is only defined over one variable.
Yeah, it's a univariate polynomial.
Mm-hmm.
Yeah. Y is the variable.
Yeah. So I think a simple example we say, suppose we have a polynomial which is y squared plus y plus one, then the representation in the field would be just the coefficients of this polynomial, which will be 1, 1, and 1.
Yes.
So this is how we how the prover commits the computational trace. He just encodes these coefficients into these as a tuple of these field elements. So now let's go over. So we saw that this group G it has to be of order P, so that the prover can commit or prover can commit to the polynomial. But usually these groups are defined over some other field F, which is field F, which has Q field elements, but it is a tuple of L tuple. So this group will be defined over some L tuple of field elements, FQ, but the order of this group is P. So yes, so those are so that's the structure. And again, Q is some Q are is the number of elements in this field, and this is some prime. And now there should now the statement says that there always exists these polynomials f1, f2 up to fl, which are the element of this field L tuple of field elements, such that if we take any two elements in the group and we try to do an operation in the group, we can just substitute that operation by these polynomials. So an addition of any two elements in the group can be just done by these polynomials. So we can just a plus b, our addition in the group can be just equal to f1, comma f2, comma f3 up to fl of a and b. So yeah, I think there. So Go, is there an addition of the polynomials, or how? So a plus b is equal to some operation within these polynomials.
Yeah, to be honest, I don't understand. So
I forgot a bit. Yes, so let me go back to the let's
is this from some?
Yeah, this is the
Right.
so this is the this recursive snarks. I think this comes. Yeah, so this was the statement. Okay, yeah, so I think the group addition of some elements inside this group is just the tuple form of these polynomials. So we evaluate the polynomials and at a and b, and that gives us the addition of these two elements in the group.
What? Yeah, wait a minute.
Yeah, it's not that necessary, but yeah, we can skip if yeah.
Yeah, I'm not quite sure about that. So anybody can. Okay, I think this part is related to so-called AGM, algebraic group model. Is some kind of security assumption. Okay, I don't quite understand what's the purpose of defining those stuff.
Yeah, I think yeah. So we don't exactly need this assumption. So yeah, we can skip over and talk about this later when we have
Yeah,
more time or
yes.
more understanding. Yeah, yeah. So this is just how these things are defined, and yeah. So yeah, so if we just take this for granted, so right now we have that the order of the group or the number of elements in the group is P, but the group is defined over group is defined or each element in this group is some L tuple over this field elements FQ. So now, as we saw before, that there might be a problem because the outer proof system uses the circuit or uses the verifying circuit of the inner proof system. And if these if these circuits are defined over different groups, then there is some incompatibility, right? Because the outer proof system needs to process the verifying circuit of the inner proof system. So say suppose if the inner proof system is defined over FQ, it does some operation in some these in this group G. Yeah, so if this verifier is doing the arithmetic in FQ, the prover P prime also has to have let me see what was the point here.
Yeah, I think this part is about the circle of Lipper curves.
Yes,
FP
yes,
and
yes.
yeah.
Mm-hmm. Yeah. So I'm trying to remember the argument. Mhm. So if C is defined over F. Okay, yeah. So let's start from the inner proof system. So for the inner proof system, as we discussed before, the prover needs some group which has the order of P, right? So that he can encode the computational trace as these coefficients. But 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 in order for the verifier to verify the proof, it has to do some operation in this group G. So the verifier would actually do these operations in group G, and it will need so it's the circuit of the verifier will be defined over FQ. So yeah, so this is the issue. So the prover is needs this group which has some order P, and is defined over FQ. Oh, sorry. So the circuit of prover P is defined over this FP, and since this circuit is defined over FP, we need a group of order P, but the verifier actually needs a group of the group with the verifier will do some operations in G, and that's why this the circuit, the verifier circuit, will be FQ. So we cannot use the same prover again because the originally this prover was doing the originally the proving circuit was defined over FP. But now if you try to do the recursive snark in this two-level system, because the prover is working with the circuit of the verifier, the prover now the group of the second prover will now should be defined over FQ. So this is not correct. Yeah. So this should be FQ. So this is the problem. So in a proof system, the prover tries to commit to polynomial in FP, and it needs a group of order P. But for the verifier to verify the circuit and to generate the verifying circuit, it needs to do the operation in that same group G, and that will lead to a circuit which needs a group of order Q. But if we try to use the same prover from before, the same prover is, yeah, so this should be FQ here. So this is my bad. So that, yeah, so now the outer prover will need the circuit over to be over FQ. So that's why there is a mismatch that we cannot use the same groups as before, because the prover, now the prover is operating over FQ instead of FP. So earlier it was doing FP for the circuit, but now it's working over FQ. Yeah, so this should be FQ, my bad. So yeah, so this is a subtle point why this problem exists, and this problem exists because the outer proof system is trying to use this verifying circuit of the inner proof system. And we have to make sure that when we commit these circuits over some field elements, these fields are compatible. So there are a couple of solutions. Yeah, I think if I went to the solution, this would be easy. So there are a couple of solutions. One is we can simulate or emulate the field. So we need operations in FQ as the circuit is defined over FP, and so yeah, so we need operations in FQ as the circuit is defined over FP, and we can try to simulate this FQ, but a single operation, if we try to simulate some operation in FQ, this will be simulated as many operations in FP. So the size of the proof or the size of the verifier would be very large. So what we're trying to do is that we try to simulate the field so that we can use the same groups again. So we can try to simulate FQ over one operation in FQ as some operation in FP. But this will result in a complicated circuit, and this will result in a large proof. And the second solution is, what if we took what if we had a group where the order of the group is P, and it is also defined over some field as a tuple of some field which has P elements. So it turns out that the discrete logarithm problem is easy in such groups, and that's why we cannot use this for commitments, because commitment should preserve the input which is inside those commitments. It cannot reveal the inputs inside the commitment. And usually the security of commitments is guaranteed by this discrete logarithm problem, that given some exponent x and given some g, which is the generator of the group, we cannot invert this x. So if we have g to the power x as h, and we only know the output and the generator, we cannot know the x from these two quantities. So this is called the discrete logarithm problem, and it turns out that if we have a group of order p, which is also defined over a field of p finite field of p elements, then the discrete logarithm problem will be very easy, and we cannot have commitments. So the problem arises from this this structure, that we cannot have group the same group with order p, and also that the group is also defined over a finite field of p elements. Because if we had that, then we won't run into this prover verifier issue. If everything was fp, then the outer proof system will just can take the verifying circuit of the inner proof system and generate the final proof. So yeah, is this more clear than before? I'm sorry to mess it up. Yeah.
Yes, so now I understand.
Okay.
Yeah.
Yes. Yeah.
So I think there's a paper called Scalable ZK circles of lived curves that the paper cited in the slides in the ZK learning, the MOOC slides.
Yeah. So
that paper, the whole paper is talking about this
stuff.
chain of groups.
Yeah. So there is there is one solution as chain of these groups, and then there is the cycle of this group. So this cycle of groups, this paper BCTV, it was released. Yeah. So we can let's talk about that. So again, the original problem started with that we cannot have a group of order p and have it defined over a finite field which has p elements. So because the discrete log problem is easy and we cannot use that for commitments, so one of the viable solutions is that we use chaining of groups. So first we have a group G1 which has of order p, and it is defined over L tuple of a finite field with q elements. So that discrete logarithm problem is difficult now in this group. So now we can try to find another group G2 whose order is q, but it is defined over some field elements with a different number of elements, which is r. So we now use these two groups, or these two combination of groups for the prover and verifier. So let's see how this works out. So say suppose we have a two-level recursion, then we can use these two groups as in this case. So now, as we discussed before, that the prover needs arithmetic over fp, but the verifier needs arithmetic over fq, right? And for the outproof system, what we can do is that use the group G2 for the outer proof system. So for the inner proof system, we use do these commitments in group G1, but for the outer proof system, we use commitments in G2. So now what happens is that the prover of the outer system needs FQ, and this is compatible with the verifying circuit, right? Because as we discussed, the prover is working with the verifying circuit of the inner proof system. So both these circuits should be defined over the same finite field. So earlier this was a mismatch as this was FP and FQ, but if we have different groups for the inner proof system and the outer proof system, then we can resolve this issue. So we are just using two different groups for inner and outer proof system, such that the verifying circuit will need FQ, and this will and the group G2 is actually the group which has order Q, but it is defined over some other field, some field with R elements. So now so in this scenario, if you want to have, say, suppose 10 level recursion, 11 level, so we need to find like 10 groups or that number of groups. So that's how we change these groups. So for 2 level, we can change G1 and G2, but for N level, we will have like N groups which can be chained in this way. So the chaining, so the latter group has to be of the same order Q, and this Q is the same number as there are the number of finite field elements in the first group, or the group is defined over such a finite field. Yeah, does this make sense? Is it clear how we can resolve this issue? So again, to solve this issue, we just use two different groups for the inner proof system and the outer proof system, such that they satisfy this relation. So now there was this concept of cycle of groups. So this was by Eli Benson, who had Starkware, and Chiesa, who was at Berkeley, and they came up with a structure so imagine that we have some group G1 which is defined over which has order P, but it is defined over some finite field with Q elements. Now we have to find a group G2 such that it has order of Q, but now it is defined over the finite field with P elements. So we are just reversing P and Q in this cycle of groups. So in the chaining, we used the order of the groups were different, and also the finite fields were now operating into another variable. But now in the cycle of groups, what we do is that for the first group, we have that the order of the group is P, and it is defined over some L tuple of finite field elements, which has Q elements. And now the other group G2, it is of order Q, but it is defined over a finite field with P elements. So now this will, so now what we can do is we can just cycle between this G1 and G2. So for the inner proof system, we use G1. For the outer proof system, we use G2. And again, for the other proof system, so this will be P double prime, we use again G1. So we cycle between these groups so that we don't run into this inconsistency. So it will be very similar than before. The inner proof is using the circuit which is doing arithmetic over FP, and the prover that therefore needs a group G1 which has an order P, but the verifier, because it does operations in G1 which is defined over FQ, the verifying circuit will be doing arithmetics over VQ. So now, since we use the second group G2 for the outer proof system, now the verifying the circuit is changed to this inner verifying circuit, and the verifying circuit is just over FQ. And this is feasible because the outer prover needs a group G2 which is order Q as we defined before, and G2 is again doing arithmetics over FP, so that we can cycle back to the outer proof system, which again uses G1 as a group, and then the circuit consistent. There is consistency of this inner verifying circuit. So yes, so we just cycle between this G1 and G2. For the inner we use G1, for outer we use G2, so that there is no inconsistency in our recursive proof system. So is this point clear? How we can use the cycle of groups and how they can. Yeah, this took me a bit of a thinking to see how it is consistent, but yeah. So again, the main point is that we cycle between these groups, and so that the verifying and the proving circuit are compatible. So there are different choices for G1 and G2. So we can have G1 and G2 as some pairing groups, but usually these pairing groups result in very large inefficient proofs. So what happens is that these pairing groups are very large, and which makes the final proof also very sorry, yeah. So these pairing groups are large, and the proof is not efficient. I think the proving time is big or something. Yeah. So yeah, I don't know why this is why this does not result in a good proof. But yes, we don't use G1 and G2 as both pairing groups. What we can do is that we can have G1 as a pairing group, but we can use G2 as some regular group, and this G2 can be a non-pairing group like the one used in bulletproofs. But what it will do is that it will give us a very large proof. So we have to make sure that the final proof is done over G1, which uses these KGZ commitment schemes with outputs in a short proof. So yeah, so a fact to note here is that non-pairing commitment schemes will always give a large proof. So if we want to, so the final proof in the recursive star system should use a commitment scheme or use a G1 pairing group, so that it outputs a short proof. But still, if you even if when we use one G1 as pairing and G2 as some regular group, this still results in a large proof which is inside the ZK star. But let's see if we can remove that feature. So another option is to have both the groups as non-pairing, and these groups are the one which are used in Halo. So these are known as pass the curves, Palas and Vesta, and these were designed for Halo proving system. So both of them are non-pairing groups, and they do give a large proof in comparison to KGZ, I think. Yeah, and I don't think yeah. So the only thing the only thing to note here is that so this is the elliptic curve. One example of elliptic curve, we have y square equals to x cubed plus t, and there is this theorem by I forgot the name, but if there exists many prime numbers, if there exist many primes q, so the statement says that there exist many prime numbers q, for which if the order of this elliptic curve is p, and this order p is prime, then we have these pairing groups, or sorry, we have this cycle of groups where the elliptic curve defined over fp is of order q, but the elliptic curve defined over fq has the order p. So we can use these combination of groups in our cycle, which we discussed before. And this is what the Halo paper uses, or the Halo proof system uses. They use these pasta curves where D is set to 5, and using one elliptic curve, we get these two different groups, which has nice properties, so that we can use them in the recursive Snark system. So yeah, so this is just a proof, like a result that if we have some prime q, there exists many prime numbers q, such that if the order of elliptic curve defined over fq is prime, then we have these two groups which can be defined over the same elliptic curve. So the same elliptic curve defined over different field elements will have different order of groups, and we can use these two groups in the cycle of groups that we discussed. Yeah, so this was the end of the recursive Snarks and things that I wanted to discuss. And then we have some shorts, like 3-4 slides on IVC. But are there any questions or any discussion points?
Yeah, I don't know if for the cycles of two elliptic curves, right? If I just my question is because we use the capital E, right, to means that the equation, there is an equation to generate the elliptic curve. So are they two capital E, are they the same curve?
Yes. So these are the same curves. So I will. Yeah. So this is the pasta curve for here too, and these are the palas. So they have the same equation: y square equals to x cube plus 5. But if you see, they are defined over.
Okay, the same
yes.
curve.
So
Okay.
yeah, same curve. But
Okay.
if you see, they are defined over different fields. So the field is different. So this is CF. This is 4A 001.
Okay. Thank you.
Yeah.
Yes.
I'll put this in the chat. Yeah, it's not that informational, but yeah, I think it will be. Yeah, and the name. Yeah, I'll put it. Yeah, I'll put it before, after. Yeah. So. Yeah. So now let's go or discuss about IVC. So IVC stands for Incremental Verifiable Computation, and this is just a fancy way of saying saying that we have this we have some computation where the computation increments in some in stepwise manner. So say suppose we have some computation where we have this function f, and at each step we evaluate this function with some inputs. So we have some initial input, which is z naught, and there is some witness w naught, and this outputs in another state, which is z1, and this is fed into the same function with now a new witness w1, and this again outputs z2, and this goes on until we get some final state, which is zn. So this is the format of IVC, which just means that we are doing some computation stepwise and with some new inputs at every step. So this is the formalism for the IVC. So we have yes. So one point to note here is that Nova uses uniform IVC. So uniform IVC just means that these functions will always be the same throughout the computation. So the functions are always same throughout the computation, and this is called uniform IVC. So the equation would be f takes some initial input z naught with some witness, and then it just iterates or computes iteratively to have a final state Z1 uh, and over some I minus 1 steps. So it computes this function for I steps, for I minus 1 steps to give some final state C1. And Nova is using this uniform IVC where the function is always the same, and the extension of Nova is, which is supernova. It uses non-uniform IVC where this function changes, and yeah, we can talk about that later. So this is a Snark-based IVC. So what we mean by Snark-based IVC? So let's just go. Yeah. So to prove that this structure or this computation was done correctly at each step, what we can do is that we can output a proof for at each step of this computation. So for the initial input Z0 and omega naught, which gives out Z1, we can put this inside a zk snark and provide a proof that this computation was done correctly. And next, what we can do is that we can have another proof system, which is pi2, which now takes this proof pi1 with some new witness omega1 to give these outer proof, the second proof. So yeah, so let's formalize this now. So again, here we have this function which takes at each step some witness, and it takes inputs which are this Z0, which was initial input at the very first step, the input at the I minus 1 step, and it gives the output as the final output Z1, Zi. And now the prover, what it does, it just takes the proof of the previous step, which was inner proof system, and it outputs a new proof, which is the proof for the outer system. So the prover is just proving that the inner proof is valid, and he is also proving that the computation for the second step or for the ith step was done correctly, which is encoded in this proof pi. So yeah, so we'll so in the next slide we'll formalize this. And one thing to note here is that we can, okay, so yes, so I'll talk about this after this one. Yeah, so what the prover pi I is doing is that it is proving that it knows a witness omega I at step I, and it also knows the inner proof, which was pi I minus 1, such that it can prove that the function was computed correctly at the ith step. So the function takes now the input at I minus 1 and witness I, and it outputs the ith state. It also proves that the inner proof was computed correctly, or the inner proof is valid. So this is again the same scheme that we were we saw in the recursive snark, but now here we have to additionally prove this function, that this function was also computed correctly, in addition to the verification circuit of the inner system. So yeah, so again, at each step of the computation, it is proving that the inner proof system is valid, and it's also proving that that at ith step, the function was evaluated correctly to some ith state. So this proof pi I is actually proving the inner proof plus the proof, the computation of this function. So is this clear? The structure of IVC in the snark? So now if you look at the circuit, the circuit does not the circuit at each step does not depend on the number of steps that we want to recurse. So again, the verifying circuit is a constant size circuit, and also the function which is evaluated at the ith step, it does not depend on the previous. It does not. It does not depend on the size of the recursion. That's what I want to say here. So at each step we have that each step is does not depend on the steps of the number of recursion steps, and at each step we are proving that the inner proof system is valid. Plus we are proving that the function was computed correctly. And so now so this snark consists of this prover and this function f, and that this we can also put the verifying circuit inside this this framework, or inside this IVC framework, but this will incur some additional computation cost or additional overhead, because we have to verify the circuit. And so if we do that, and the Nova paper actually does put the verifier inside, and they find out that their computational overhead is like they have to do some scalar multiplication, which is 12k constraints. They have to do hashing, which is 3k constraints, and this hashing includes the hashing from the random oracle. And even if once they put the verifier inside the inside the IVC, they incur a lower cost than Halo, and this cost is like 7 times lower than Halo. And that's why Nova was so popular, and Nova has been catching so much thought and so much discussion, because it reduces the computation cost and also is much faster. Yeah, so are there any questions about IVC or the things that we discussed, recursive snarks? And is it clear how what we discussed in recursive snarks can be just be used in this IVC, where we just have this outer proof, which proves the inner proof plus the computation of some function f? And so one more thing to note here is that the verifier just that the public parameters in this framework are z0, or the initial input state, zn, which is the final input state, and the number of steps it was run. So these are the public inputs, and the verifier just uses these inputs plus the final proof to verify whether the circuit is valid or not. So the verifier does not know the final verifier does not know the initial steps of the computation. So if we go into the paper and see, we see. Yeah, so again, you can discuss this the same concept of completeness, and I think also knowledge soundness in this IVC scheme. Yeah, but I think it will be a bit complicated there. So yeah, so that was it for the presentation. I think next presentation we can talk about folding schemes. So we'll go through folding schemes, then folding schemes for NP, or how do you construct a folding scheme in this R1CS, and then I think in the So that will take again one more lecture, I think, and then in the last lecture we can have, or last presentation we'll have, we'll talk about how Nova actually uses these concepts of folding scheme and IVC to compress the proof. Yeah, I will share the links for the lecture that I referenced and also the past the curves. So if there are no questions, then thanks for joining, and let's meet again. Yeah, so next Friday I might be traveling for each CC, but I'm not sure. Yeah, so we can schedule some time with which we are all comfortable.
Sorry, what about next topic?
No, so yeah, so next week, I might be traveling to each CC.
Oh,
So
okay.
yeah,
Oh.
so yeah, we can discuss some other time or whatever works for everyone. Yeah, so for next presentation, I was thinking I can go over the folding schemes, R1CS, relaxed R1CS, and how to actually, to have the folding scheme.
Okay.
And then in the last one, we can do like only how Nova actually uses these to compress the proofs or the actual algorithm or structure of Nova. Yeah, I think that will be complicated.
Okay. Okay.
Mm.
Okay, thank you very much.
Yeah. Thanks for listening. Thanks for coming. Yeah. So, all right, guys. Let's meet up next time and see you soon. Bye bye.
Okay, see you.
See
Bye.
you. Bye bye.
See you guys. Bye.